communication in signal processing in Doppler Flowmetry. Here this is the outline of my talk. I will discuss the motivation for our studies, then I will try to talk about Doppler Flowmetry aggregation principle and the traditional signal processing for this method, and then I will talk about the proposed approach, explaining studies conducted and the results. So the microcirculatory tissue system is the main object of the study by Doppler Flowmetry. It's a complexly organized system that changes between blood and tissues necessary to provide tissue metabolism and removal of metabolic products. And microcirculatory tissue system is first link with the many critical conditions, and that's why it's so important to evaluate its functional state. So, Doppler Flowmetry is a non-invasive method to estimate the total local microcirculatory blood perfusion. It's based on the emission of the beam of laser light carried by optical fiber and the recording of the scattered light from moving red blood cells. And the results, the results in signal is directly related to the number of red blood cells in the sampling volume and the velocity of the movements. Previous studies have shown the presence of rhythmic oscillations in the signal recorded by Doppler Flowmetry, and by tracing the characteristic frequencies, the overall frequency band recorded by this method was divided into 5 intervals, each of which correspond to the blood flow, different blood flow regulation processes. And pulse and respiratory oscillations related to the influence of heart activity and movement of thorax on the resulted microcirculatory blood perfusion recorded. And myogenic oscillations mirrors the vascular smooth muscle cells reaction on the changes in transmural pressure. And neurogenic sympathetic vasoactive vasomotor activity can be evaluated by neurogenic oscillations in this signal, and the slowest blood flow rate mirrors the vascular tone regulation due to the endothelium activity. So, in Doppler Flowmetry, coherent light vertical tissue will be scattered on the moving particles, it's predominantly red blood cells, and on the static tissue structures as photon rays in random pattern, and light that had been scattered on the moving particles will undergo the shift in the frequency connected with Doppler principle, and the light that had been scattered on the static structures will remain unchanged in frequency. And then when limited light will be recorded on the photodetector, the optical photomixing of this light that changed and unchanged in frequency will be result in the appearance of stochastic photocurrent, power of spectral density of which is directly proportional to the red blood cells concentration and the average velocity. And in the traditional Doppler Flowmetry signal processing, the integration of the Doppler shift power spectrum is conducted over the frequency, and in this case, usually the light frequency range is used. It's usually from 20 Hz to 24,000 Hz. Additional preliminary studies have been conducted, which were aimed at comparison of signal recorded by Doppler Flowmetry from the tissue of the volume from 1 to 3 millimeters, and the signal of blood velocity from the separate capillary recorded by the method of high-speed video capillaroscopy. For these measurements, the video capillaroscopy system has been developed on the original software, which allows to evaluate the blood flow velocity in the single capillary. And here you can see the results. It's a graph of blood flow velocity in the single capillary. And it was shown that these two signals recorded by Doppler Flowmetry and video coperoscopy are proportional to each other, which proves that Doppler Flowmetry signal largely dependent on the blood flow velocity in capillaries. In this regard, the aim of the study was to implement and test a new signal processing approach which allows to evaluate the distribution of blood flow signal over the different frequency ranges. As it was previously shown in previous studies, that the frequency range of signal integration is influenced on the signal obtained, and sometimes it's more preferable to integrate the signal over the narrower frequency bands. And this method allows one to obtain the signal from different blood participation structures with corresponding different blood flow velocity, and thus obtain new diagnostic information. Experimental studies have been conducted, and the in-house built Doppler Flowmetry setup was developed, and this setup includes single mode laser source and two photodetectors. And the delivery of light to the tissues was conducted by optical fibers, and the system also included analog amplifier with analog to digital converter and data acquisition card. And laser Flowmetry signal has been processed by an approach based on the fast Fourier transform with the following frequency ranges of the signal integration. Experiment included two parts, and first part was study of the occlusional test influence on the blood flow distribution over different frequency subbands of Doppler shift of the signal, and the occlusion was carried out by clamping the forearm with the diameter half with a pressure of 220 millimeters, and it was conducted in 3 stages. First of which it was baseline experiment for 3 minutes, and then there was occlusion for 3 minutes, and then 5 minutes of post-occlusive reporting. The second part of the study includes study of local pressure influence on the laser Flowmetry signal distribution over frequency sub-bands, and special tooling has been developed and 3D printed to applied pressure on the tissue. It was placed coaxially to the optical fiber, and weights were added evenly until the pressure will reach 40 kilopascal. And then there was subsequent unloading of the tissue in the same order in which loading occurred. And the study was done for approximately 15 minutes each, and in all the studies healthy volunteers participated. Here you can see the results for the first part of the experimental studies include occlusion test, and the results is presented in the time result graph with corresponding Doppler shift frequencies, and the amplitude of the signal is coded into the forward bar. And you can see here that after removal of occlusion, there is the increase in the amplitude of the signal occur in the frequency bands from approximately 800 Hz to 3200 Hz. And this result, you can see also in this picture, it was placed by dots. And this result can be potentially explained by post-occlusive reactive hyperemia when the increase in the number of fast-moving red blood cells occurs in the probing volume. He presented the results of the second part of the studies with local pressure loading of the tissues, and it was shown that the blood flow signal starts to decrease when the pressure reaches 5 kilopascal, and at the same time it was shown that in the low frequency diapason up to 1000 Hz, the increase in the signal occurred during this pressure loading, and it can be connected with influence of local pressure on the blood flow signal, because when the pressure is applied, it slows down the blood flow and more slowly moving red blood cells occur in the body volume. So the proposed approach to analyze the laser flowmetry signal allows obtaining new diagnostic information on the macrocirculatory blood flow and the investigation of the macrocirculatory index distribution over the different frequency subbands could potentially have a diagnostic value in conditions associated with macrovascular disorders. So I would like to thank this research fund that supported this work, and also our colleagues and collaborators, and thank you for your attention.
Thank you very much. So the paper is for discussion. Question or comment? So we show result, the second result.
This one?
Next. Sorry, I'm not familiar with field. What's the index of the wireless citation?
It is a parameter recorded by laser flowmetry. Actually, here. It is, here. It is a signal obtained by this method, and it's actually measured in RG units, because it is proportional to the red blood cells concentration and average red blood cells velocity. And you can see here it's measured by integration of our spectral density of the obtained optical signal on the photodetector.
Okay, I'll go back to the result. So I can see that the data changes continuously around 10,000. So
yes. It's connected with experiment, because this experiment was studied. The influence of local pressure was studied in this signal, and we added weights to provide the pressure. So each of them have here, and in this part of the study, we added weights, and then we unloaded tissue with weights. And here, I think that it's connected with removing of weight, and when the pressure decreases, this here the signal rose significantly in this stage.
So the title of your paper is the use of the Doppler velocity.
Yeah.
Okay, so how much is the velocity of the blood cell in the direction of movement? Can you measure?
Actually, this method provides the information on the signal obtained is measured not in absolute units yet, unfortunately. It's RBT units, and they carry on information about both the average velocity and the red blood cell concentration. So we cannot measure actual velocity because it's a complex signal. But here it was shown that during this experiment we measured the blood flow in the separate capillary, in one capillary. And it was shown that we measured simultaneously the signal of laser flowmetry and the signal of velocity. And it was shown that they really high correlated to each other.
The input light direction here and the reflected light also. So the can measure the velocity. The component of velocity is the vertical and horizontal.
Yes, the magnet is not measure the actual velocity; it's measure the Doppler shift of the light when light is scattered from moving object. It's undergoes a shift in frequency, and this is what actually is measured by this method.
Okay. Any questions? Okay, let's speak again.